Okay. All right, let's get started here. And assignment 2, last time I thought assignment 2 would have been submitted by today, but it's not. In fact, it's due tonight at midnight. So I'm going to wait until Wednesday, and I'm going to give you until midnight tonight to work on those problems yourself and get those submitted before the deadline. And then on Wednesday, we'll look at the solutions for assignment 2, and then on Monday we'll have the quiz, which will resemble assignment 2. All right. So what we can do today, where we left off last time, which is in lab 7, and we completed this problem here, which was to implement the function my maximum. And one of the things that we learned about in this exercise was how to use arrays. And so this is an example. This first argument to the function my maximum takes an array called A. It's a sequence of integers, of some unknown number of integers. So actually that's what we need to do. We have to pass in that information to the function, how many integers are in the array A. And so we solved this last time, and we used assertions to test our code, and we used the process of test first software development, where we built our test cases before we tested our implementation. And we'll continue to use that strategy in the next 2 exercises. But the thing that the purpose of this next exercise actually is 2 things. One is to understand this reference here, and the other thing is to understand vector. So vector is a class, just like string or just like bean jar, and the classes that you're defining in assignment 2, and that you did in lab 6. So you were in lab 6. You're defining and implementing classes. In fact, vector is a class, and it's a class that is used as a convenient wrapper around this array. It gives us functions that we can call conveniently, rather than doing a lot of work manually. It gives us a lot of functionality. And that's actually similar to that number class. Remember that number class that we worked on? I think you did it in the lab. That it's just a wrapper around an integer. It has these convenient functions like is prime and is divisible by. In the same way, vector is a wrapper around an array, and it just makes it more convenient to work with arrays. Now, it's not a class that we're going to implement. It's a class that's provided to us by what's called the C++ Standard Template Library, or STL. So we'll look at how to use this vector, which is essentially an array with this convenient set of functions that go along with it. But notice there's some additional syntax that we need to get used to here, and that's these angle brackets that follow the data type. So this is called a template class. And you see here, this is an array of int. Now, if we wanted an array of string, we would put a string here. Or if we wanted an array of double, we'd have to put double here. We wanted an array of bean jar, then we would put bean jar here. And so in this function, we have the array that's getting passed in. We have to state the data type, the type of thing that's stored in the collection. We can call this a collection. The array is like a collection. A vector is, we call it a collection, and that's a common word that's used to describe these things. They're also called data structures. They're collections of data, organized in a certain way, so they have a certain structure. And but now this vector v, just like the A here, the vector class is written in a way that allows it to work with many types of data types. And for instance, it works with int. And it's possible to define a data type that vector wouldn't work with, but we're not going to get into that. In fact, that's a topic that we get into in an advanced course called data structures. We look at that. So in our data structures class, which I'm teaching next quarter actually, we look at how to implement vector. But we're not going to do that here. We're just going to use vector. Now this n here, this is not the size of the vector, this is something else. Let's see, we call the function func. And let's read through the problem statement here. Provide an implementation of the function whose declaration is shown above. The first argument of the function is a vector of int, and the second argument is the number of consecutive integers to append to the vector. So in other words, the function is going to append this sequence of integers to the end of the vector. So it doesn't matter what's in the vector. It could be empty. It could have 1,000,000 integers in it of any integer value. But what we'll do is onto the end of the vector, we're going to append these n+1 values. And we say n+1 here because counting starts at 0, right? And here's the hint, use pushback. So pushback is the function, that convenience function that lets us append a value onto the end of the sequence of values, onto the end of the vector. See, the difference here is this array is a fixed size. So there's no pushback. We'd have to write a pushback function. In fact, how do you write the pushback function? We would have to allocate a new array that has size 1 more than the array coming in, and then copy values into the new array, destroy the old array, and then work with our new array. So that's, you see the extra work you need to do? So these arrays are of fixed size. They're not containers that have a variable capacity. But vector is different. The array is a variable-sized container. It can have 0 objects or any number of objects, you know, respecting the memory limits of the machine. And then we have this pushback function. So if the array has 3 things in it, if the vector has 3 items in it, and we call pushback, it'll then have 4 items in it. So it's flexible. Its size is flexible, and that's not. Once again, that's not the case with an array. An array has a fixed number of values, and of course we need to remember what the fixed number of values are by passing this around, or keeping track of the number of elements in the array. All right, so let's go ahead and implement this thing, and I'll just copy that function signature. And let's see, just want to make sure I got this recording here. Yeah. All right, so I've created the folder Labo72, and let's go ahead and do this. Oops. So here's the function signature. Then we have a main. And I think the compiler will take that. Actually, is it an int? Maybe it won't take a void. We'll return an int here. But I'm going to omit the arguments here, the 2 arguments, the standard arguments, because most compilers will accept this version of main and work with that. Now, to use this vector, we need to include a header file. It's easy to remember. It's just vector. And let's also remember the using statement. You know, I'm going to leave out the using statement just to show you why that's needed, just so that you can remember what's going on there. I'll comment it out, show you what we need to do if we omit that. So we're going to have tests, and we're going to print all tests passed at the end. Is that going to compile? Well, no, because we commented out this line here. So why will this fail to compile? Well, there's two reasons. This name is in the STD namespace, and this name is also in the STD namespace, standard namespace they call it. So we have to tell the compiler to look in that namespace. So we just prefix those identifiers with the namespace name followed by 2 colons. So that's a way of telling the compiler, we need to give the compiler that information about the namespace. Exactly, exactly. When we do using namespace std, we're saying import all the symbols that are in the std namespace into our default namespace, which is an unnamed namespace. So this is, in fact, you'll see some programmers that do it this way because they don't want to, quote, pollute the global namespace. See, when you do using namespace std, you expose all of the symbols that are in the std namespace. You expose them in the global namespace, which we're working in, or the unnamed namespace. Not sure it's called global namespace, but the unnamed namespace. So they use the term polluting, right? So we're exposing more symbols than are necessary inside, you know, our context. So we're polluting. We have too much stuff. So you'll see people that that just do this, and maybe the project requires this. You know, you're in a team, and they have standards. They follow the standards. Say, this is what we do. We don't import namespaces. You have to specify them because they may have several namespaces in their own project, and they're keeping track of, you know, what they're trying to do is avoid collisions. So naming collisions. So I called my function func in this namespace, and someone else called the function func in another namespace, but we're not importing each other's namespaces with a using statement. If I want to use, you know, your func, I'm going to use the namespace prefix on your func, so it won't collide with mine. That sort of thing. And you'll see this is very important in other programming contexts, not just C++, like C# in particular, and Java as well. The very namespace-rich, you know, the concept of a namespace is central to the working in those languages. So you have to learn how to do that. And it's not the case for other languages like JavaScript, for instance. They don't have such a concept. I'm not sure about Python. I don't work in Python enough. Maybe some concept of a namespace in there, but there's lots of this happening. All right, so let's go ahead. I think this will compile. And I think it'll run, and all of our tests will pass. We have no tests, so it's easy to make no test to pass. Cout is not a member of std, but we know that cout is a member of std. So what's the problem? What's that? Yeah, that's right. We need to include that header file. Exactly. So that the compiler is not, you know, searching all header files in existence to find cout. It only searches the header files we tell it to search. And you get this in other languages as well. You know, I work a lot in C# now, and you know, in .NET, which is actually just .NET, so all the Microsoft languages, C# and VB.NET and C++, that you tell the compiler, you know, which files or which, what do they call it? They call them assemblies in .NET. You know, which assemblies to search to find that symbol. Now, don't search every assembly on the system. Just search the assemblies I tell you to search. So that's like this. We're telling the compiler, just look here. Okay, there we go. Let's go ahead and do this now. So we're going to append. Let's do our first test and watch it fail. So we want to do test first, development. So we can write a test, make it fail, and then we'll implement and then see the test pass. So let's create a vector of int. We'll call it v1 for the first vector. And let's push back a number, say 3. Now the vector v1 at this point, you know, you can think of it like this. Let's do some notes here. Here v1 is going to look like the following. It's just going to be like the empty set. There's nothing in it. Then after this pushback, v1 will look like this. Actually, this is not a good symbol. It's not, because it's not just a set. Actually, it's an ordered sequence of values. And I think in math they use parentheses for that. So the curly braces are for sets. Sets are not ordered. And let's go ahead and, you know, let's make it look in a typical way here. Let's make this say -4. You know, because we're learning the subject, let's verify our own understanding with some assertions. This isn't going to be testing our function. This is just verifying our mental assumptions. And you know, I do this all the time, and I recommend that you do it too. That when I'm working in, say, a new API or using a new function that I'm not that familiar with, I've got some mental assumptions. Maybe I read it in the documentation, maybe I didn't. Maybe I'm just guessing how the function works. And but in either case, because I'm not familiar with this API or this function, that I'll code up some assertions just to check my understanding, so that I don't have to go into lengthy debugging. You know, an assertion will fail and say, oh, I don't understand what the function does. So let's put some asserts in there. Oh, before we do that, let's remember that's an include also. All right, let's go ahead and do that. Now v1, let's see. Oh, v1 has a size function. Let's call the size function. It should return 3, right? Because oh no, it should return 2. Sorry, it has two integers in it. So there's the first assertion we can try. And let's try the other assertions. Let's do v1 of 0. That's the first position of the vector. v1 of 0 should be 3. And v1 of 1 should be -4. Once again, we're not testing our function yet. We're just testing our own. We're just testing our own understanding and knowledge about this new data structure or this new class or language element. There's a lot of ways of saying it, isn't there? So that's yep. Who can debug that? I'm not going to look at it yet. I think I know what it is, but I didn't read it yet. Who can figure that out? Where's the beginning of this? It's here? Is that where I did it? Wait a minute. Let me just do that again. We got no, this is vector.h here, in a sense. So you can drop the .h on these. Well, actually, the files are there without .h's. What's the problem? Yeah, the problem is the namespace. Exactly. We didn't qualify the word vector with std here. See, we used a name that the compiler said doesn't exist. Remember, we're qualifying our names with namespace prefixes now. We'll do it this way once, which, by the way, a lot of people consider good practice. So, in fact, we could have done it this way through the whole class. All tests pass. So these assertions are good. You know what? Let's make sure that we're running the code. Actually, let's see that this should be wrong, right? So assert 1 is 4. That should fail. Let's make sure that we're doing this right. Oh, there we go. Assert v1 of 1 of 4 failed. Okay, so we're good. We're good there.
Can you explain that assertion, like or that syntax?
This right here? Okay, let me. Oh, you know what? This isn't taking std. Assert is not, in the standard namespace. I never knew that before. Let me tell you what assert. Assert is a function.
Right.
Now, let me make it easy for you here. I think. I'll try to make it easy. If I do this, now true is Boolean true as a value. True as a value. So we could do it like this, or we could do it like this. We could say bool. This is my true false value, and let's set it to true. See what's going on there? Assert is a function. We call the function. The function takes a Boolean argument. It has one argument, and it's of type bool. And when the function runs, if the argument evaluates to true, assert returns quietly. It does nothing. But if the argument evaluates to false, then assert prints a statement with a line number and the text and the the contents, the symbols that are used in that argument to assert. Actually, I think assert is not in a namespace because it's a macro. Yeah, but I'm not going to go into that now.
Well, with our vector v1, you have assert v1 and then some value 0 set is 3. What is this?
Well, look at that. You got to look at what's going on here. This is an expression. Expressions have type. Some expressions evaluate to type string. Some expressions evaluate to numbers that are of type double. Some expressions will evaluate to type my bean jar, something like that. This expression, the expression that you use inside the argument to assert must evaluate to bool. Actually, if it evaluates to int, it's accepted, but that's kind of unfortunate in C++. In other languages, it wouldn't be like that. So the expression has to evaluate the true. And look at the expression. It's comparison. You know, look at what V10 is. Compare it to 3. Is it equal to 3? That's a question. That's a true-false answer to a question. So whenever you see this double equals, you should think comparing. And the result of comparing is true or false. Either they're equal or they're not equal. So that's the data type. You could also do something like this. That's comparison. So something on the left is greater than or equal to something on the right. That's a true-false answer to that question. So these are called comparison operators, and when they're used to form these expressions, they evaluate to true or false, and that's a data type that has to be passed into assert.
In your comments, V1 equals 3, V1 equals, shouldn't you have V1 with a sub-0 to establish it as a different from the V1 sub?
No. This is a vector. This is not an element. This is the whole thing. So this V1 is in fact a collection, an ordered sequence of integers. So I'm showing it equal to something in parentheses. So this is in fact, this is V1 of 0, and this is V1 of 1.
That's what I was saying. Shouldn't it be that you said the V1 of 0 and the V1 of 1 be after the V1s? Because you have that in your assert.
Oh, down here?
You have your V1 of 0. Shouldn't
Yeah.
that represent the V1 equals 3? Or is that just too much?
Well, no. This is not, remember, this is not V1 equals 3. No. This is not V1 equals 3. Like if you have the set of 3, okay? If A is the set of 3, does that mean A is 3? No. A is the set of 3. Vector is, V1 is not 3. It is the container that has one thing in it, which happens to be 3. Yeah.
So it's more of like a list then?
It's a list, exactly. It's a list. Did you get it? Okay. Well, if you don't have it 100%, then it'll come to you as you think it through it more. All right, so let's go ahead and try this. We added some things in there. Let's try that. Just to make sure we got that. All tests passed. Of course, if we pass in false, it will fail. Now, the other thing to keep in mind is, you know, just to hammer this home here. If this were a, say, a double, you know, it actually might work. So let me wait on that. Let me try string first. Make sure that we get a failure here. Now, what do you think is going to happen now? In fact, we'll even make it true. What's going to happen? But the data type is wrong. We're passing a string into a function that expects a bool. So it won't compile. We can't run it because we can't even compile it. Error. Could not convert my true-false value from std string, otherwise known as, to bool. And we'll skip that otherwise known as part. So it tried to convert it. So look at what's going on here. There's some automatic conversion happening. That's why if you pass in an int, well, it'll be okay. Watch this. If we pass in an int, it probably will compile. Let's pass in a 1. And the reason is, as you said, it couldn't convert the string to a bool, but it can convert it into a bool. So this, in fact, will pass. There we go. And we pass in a 0. You see, integer, if the integer is 0, it's converted to Boolean false. Any other value is converted to Boolean true. So this will fail. Assertion failed. Now, let me hammer that home. Let's suppose we pass a -1 in there. Is that going to fail or succeed? Should pass, because anything that's not 0 is considered true. Make sure I save it. There it is. So this is good. Now what about a double? Will the system convert a double to a bool automatically? The compiler would generate machine instructions that do that conversion for us. Do you think that that's going to work? I don't know. Okay, I don't know. So I would have to bet, and let's see. Oh, it built. You see that? I'll try it again. What happens if I put a value of 0 in there? So there's this thing called automatic data conversion, which the compiler does for us between certain data types. So 0, it actually correctly converts 0 to false for doubles. But for string, it fails. It can't convert to string. But when we had that in there, whoops. When we had this in here, let me go backwards. See if I just hit U a whole bunch of times. Just for your information, that in scripting languages like JavaScript, that the string true will be converted to Boolean true. So this, in fact, would work if you were in JavaScript. All right, getting off on some tangents here. Any other questions on this? How assert works? All right, let's get to the main task, and we're going to call func with our vector v1, and we're going to pass in, say, 2, just to make it easy to figure out. I'll pass in 3. And this, I'll just put a little comment here, the following tests are just to verify our understanding of vector. And this test here, these tests will be to verify our implementation of func. So after we run this, that means what we want is for v1 to equal 3, -4, 0, 1, 2, and 3. Right? So we're calling func, so we're appending 0 through n. But n is 3 in this case. So we're appending 0 through 3. We can copy these. Now the size will be 6. And these values should continue to be, you know, v1 of 0, v1 of 1 should be 3 and minus 4, just like that. But but let's test for the other positions. So this should be a 0. This is 1, 2, and 3.
Should we compare two though and not?
Oh yeah. We don't need this. Yeah, thank you. We'll just revert that. Very good, thanks. Fix the comment. Look at that attention to detail. That's what I want you to do. That's what your boss wants you to do when you graduate and get work. Okay. Is this going to pass? I hope not. If it passes, we're in trouble. Right? The first test, we write the test before we implement the solution. This should fail. It better fail. Okay, it failed on the first assertion, which is that the vector is of size 6. So good. So we're going to get to that, and then we'll get to these. Now we need to append n plus 1 values, so we use a for loop. And we'll start at 0, and we're going to go up to and including n. And then we take the v that's passed in, and we call pushback. We're going to push back n. No, not n, I. That look good? We start at 0, and we go up to and include n as a good number. We're going to pass in 3. We want to push back 3. And we're going to push back I here, not n. I think that's going to pass the test. We did it. We can also test some, the other situations where maybe the vector is of size 0. Let's try that. Let's have another test in there. Oops. Let's create another vector, v2. And v2 is empty. Let's test our understanding of that. We should have size of 0. And then we'll push back. We'll take v2. Whoops, that's v1. Remember that it's dangerous to copy your test code. v2 of 0. I'm sorry, v2 dot pushback zero. Now v2 should equal a list with one value in it. And now let's do the assertion. The size should be 1. And the value should be 0. Danger, copying test code. Gotta change that. And that should be the value 0. All tests passed. Any questions on that?
When you say B2 of 0, what does the of 0? It's the bracket. What does it mean?
That means the first item in the list. The item at position 0. Now positions, it's like a street. You have a street with houses on it, and the houses have street numbers. But unlike human society, computers start counting from 0. So the first house on the street is house 0. The first item in the list is item 0. It's like a label. It's a label for the first slot. So this syntax here means look at slot 0. This says look at slot 5. Now slot 5 is the 6th slot. The 6th slot should have a 3 in it. Is that okay? All right. All right, now comes to the hard part. What is that? Let's take it out and see what happens. Is anyone want to venture a guess? Anybody who's been doing the reading? What happens when we get rid of the ampersand in that first argument? This is very important, not just for C++, but all the languages. You have to be conscious of this. When you call a function and you pass in some symbol that represents something, like an integer or an instance of a class, that there's two ways that information can come into the function. I'm going to simplify it, say 2 ways. One way is that the information coming in, that we make a copy of the information. And we access and operate on the copy. And the other way that we handle information coming into the function is we don't make a copy. We retain a reference to the original data that the caller has. And when we read and write to that symbol, we're going to read from and modify the data that the caller has access to, that the caller created. We're not making a copy of what's getting passed into us. We're keeping a reference to what was named for us. So the ampersand means I want V to be a reference. It's a name for the vector that's being named, as in my argument list. And then when I operate on V, I'm going to operate on that vector, that data, that the calling code created and named and told me about. But we took the ampersand out. So that means the compiler is going to generate code that makes a copy of the vector that the caller is passing in. That means that when we push back I here, we're modifying the copy. And then when we return to the caller, we're discarding the copy. And now the caller has an unmodified V. If that's the case, which assertion should fail? There's the first assertion right there. Is that going to fail? Oh, we didn't call func yet, right? So what we're talking about is changing the behavior of func. So we didn't call func yet, so this assertion won't fail. We call it there. So after we call func, then the size goes from 2. The size goes from 2 to 6. So that should fail. If our analysis and our understanding is correct, that should fail. Let's see if it fails. There it is. You see, I want to get you thinking in this sort of procedure, this process that I'm trying to show to you. You don't just run it. Just stop and think and say, I know it's going to fail. Let me reason through it. And you get to the point and you say, that's it. This is what's going to happen. And then when you have that confidence, I mean, you know, you never have full confidence. Even when I'm up here running things, there's always a shred of doubt. I always have. I mean, because some things just go wrong, you know, and I forget stuff. And so you reason as far as you can. You get to the point, you make this prediction, then you run it. It's like a scientific experiment. You have a hypothesis, you set up your experiment, you run it and verify your hypothesis. Don't forget the hypothesis. If you're going to be playing with code and experimenting, if you leave out the hypothesis, you're not going to learn anything. You're just going to be like, you know, I don't know what, just playing around. Okay, so that's the meaning of this reference. Let's put it back in there and fix the problem and get the test to pass. There we go. How are we doing on time here? So that's it for the second exercise, plus a lot of talking about. Fortunately, we had time to go into it. They go into a lot of little details at that point. Hopefully that's more clear for you. I think we can get one more done. Let's do exercise 3. I'll make a folder for it. Oops. All right, let's contrast this here. Let's suppose we did this. We brought this using statement. Is anything going to break? No, everything's okay. That's because it's all right to be redundant. We can import all the symbols. We don't get a conflict. It's only that we don't. It's just now unnecessary. Now, one of the benefits of using that using namespace feature is that it shortens up the line, see? And this is a lot easier to read, and that's why I use it a lot of the time. I don't always use using namespace std, but I do. But I usually use it, especially with these small programs. It's just a lot easier to read. Not a lot easier, it's a little easier to read. Let's see if we get that to work here. Okay, now it's all right. Now we have a different function to implement. And let's start from scratch. Here we go. Okay, we're at the starting point. All right, suppose a vector v contains a sequence of integers ordered from lowest to highest. So something like this. 3, 6, 7, and 12. They're in order. They're going from lowest to highest. The sequence is ordered. And oh, there it is. Yeah. For example, the sequence V might be 3, 6, 7, and 12. Write a function called insert that takes this vector V as a first argument and an integer k as the second argument. The function inserts k into the vector so that it preserves the order of the elements. For example, if V were 3, 6, 7, 12 and k were 8, then after calling the function, V would be 3, 6, 7, 8, and 12. So 8 would be inserted in the right position. Write test code to thoroughly test the function. Use assertions. All right, so it's called insert. Let's call insert. So we have a vector V. We're going to want reference, right? Because we're going to modify V. And we'll insert, well, the problem calls for k. I mean, n would have been all right, but, and we're going to need some test vectors. Here's one. Let's put a minus. Well, you know, let's use the numbers that are in the web page. The 3, 6, 7, and 12. Whoops. Then we push those back. Then we're going to call insert. We're going to pass in V. And let's insert 8. And then we'll have our assertions. So the size of V should be 5. And V1 of 0 should be 3. Let's test, you know, every position. So this will be V of 1, V of 2, V of 3, and a V of 4. It'll be 3, and we'll write it out. Let's write it out here, just to make it a little easier to look at. So V1 is the sequence, which is an empty sequence. When we push back 3, then V1 is the sequence of a single value in it, which is just 3. When we push back 6, then we have 3 followed by 6, and we need to push these in the right order so that they're, because the precondition is that, actually we have a precondition. When insert is called, we're going to assume that the values are in the right order. So that's a precondition. We could test for the precondition. I didn't ask for that in the problem statement. So I would say it's optional. But we could test the precondition. So here, you know, the precondition is they're non-decreasing. We could test this. Is that a good quiz problem? Test that the precondition is correct. So you'd have a loop in here, and you make sure you look at adjacent values. Is V0 less than or equal to V1? Is V1 less than or equal to V2? And you do that all the way up to, you know, size -1, size -2, something like that. Those actually, that's exactly the last two pair of indices that you would use. Okay, so let's go back here. And then we have 7. Then we insert, so we're going to insert 8. So V should look like this. 6, 7, 8, and then 12. It should stop and insert right in there. So this should be 3, 6, 7, 8, and 12. There we go. V is not declared in this scope. Line 22. Oh, there it is. I just jumped right to line 22. V is not declared in the scope, line 23. Look at that. Should it fail or pass? Should fail, right? The first assertion. Look, this vector here, at this point, how many items does the vector have? 4. Okay. When we call insert, what does insert do? Look up there. What does insert do? Does it do nothing? It does nothing. Sorry. And so that means V1 has 4 items in it, right? So that'll fail right there. Good. Make sure that's saved. If I made sure that's saved, I'll make sure that that's compiled. There it is. It failed on the point that we were expecting. Good. Now we wrote the test case. Well, we wrote one test case. We could write more, but we don't actually have time in class, so we got to just get to the end here. Let's figure out how to do this. Well, I've solved the problem before, so it's easy for me to figure out a solution. But is there someone that wants to suggest an algorithm to use here? A process? Do we use pushback? I mean, how else are we going? We need to, the vector needs to have size 5. We only have size 4. So we got to add space in the vector. How do we do that? Well, we can push front. No, do they have push front? I don't think so. Just push back. And maybe there's some other functions that we can call. But I think pushback is sufficient. I don't think the book covers any other vector functions that can add one slot to a vector. I think pushback is the one we need to use. So we could put anything on there. Let's push back k. I think that's a good value. We could push back 0 if we want, whatever. It depends on how we implement this. So now we have a vector that's now 1 bigger. But they're just not necessarily in the right sequence. So can you visualize the solution at this point, how you would do it? You're going to copy values. You know, you're going to start at the end of the vector and you're going to copy values one slot forward until you find the place where k needs to go. Well, we could do it, we can use a for loop. We'll use a while loop maybe. So we'll have our index I. Let's see, I gotta explain this. Do you see what to do here with this vector here? Let me see if I can explain it. What that's going to look like with an eye on the time here. So we have 3, 6, 7, and 12, and we need to put an 8 on there, inside there. But what we need to do is create a new slot here, see, and then push 12 into it. We're going to kind of push 12 into that slot, and then look at this slot. And then when we look at that slot, we look at the value before it. Is that less than or equal to k? If it is, then we've got our place for k.
As long as the value after it's also less or also greater.
Yeah, that's right. So we start here, exactly. We start here, we start at the end, and we look at the value preceding it. Is that value bigger than me? Is it bigger than k? If it's bigger than k, let's move that value into this slot that we're looking at. Now I is what is right down here. I is that index that we're examining. So I would be 1 dot size minus 1, right? Remember, this is position 0. 1, 2, 3, position 4. There's 5 items. We want to start by looking at position 4. We got to take the size minus 1. So I is going to be pointing here when we start the algorithm. And we look at I minus 1, assuming that I minus 1 is bigger than or equal to 0. Because if we're at the front, and that's what we have to test actually. Those are the other tests we need to run. If we're pushing back, say 1 under this vector, we're going to get all the way down to 3, and then we're going to try to look at the one before it. But wait, there is nothing before 3, and so that's where k goes. And we'll need to create a test for that. But we're looking at the common case first. That would be call it boundary case. It's the uncommon case. The common case is that k is going to go inside the vector somewhere. The two uncommon cases are the vector goes in the very front, the value goes into the very front or goes into the very last slot. Another case that we need to consider is when there's duplicate integers in the vector. And let's suppose we want to insert 7 into this vector. Well, there's already a 7 there. We just have to make sure it handles it well. All right, so once we move 12 out like there, then we're going to write the 8 in here. So that's the algorithm. Maybe we'll use a while loop here. So while I is bigger than 0, and the reason I do that is because we're going to look at what's in position I minus 1. So I can't be less than 1. So we'll do the, let's just, we're just guessing here. I don't know the whole solution yet. I know that I just have this sort of fuzzy solution in my head where we're moving this index down the list, and wherever I is, we have to look at what's in I minus 1. So let's go ahead and do that. If what is in position I, if that is less than what is in position I minus 1, then we do something. Else we do something else. So we can conclude if I minus 1 has a value that's bigger. Oh no, I'm doing this wrong. Sorry, this is K. If K is less than, so we start by putting K in slot in the last slot. See, here I is set to V sub I V1 size minus 1. That means, see, we push K into the last slot. So K, when we start this loop, K is at position I. See, we put K in the last slot. Then we set I to the index of the last slot. So K is in position I. Now, if K is less than the value that precedes it, the value that's in position I minus 1, then the last slot is not a good place for K. Let's see. So what we'll do there is we'll move. I know it's hard to follow this. Actually, it's hard to explain it. Let's move what's in position I minus 1. Let's move it into V of I. Let's move it into the I slot. So basically, when we start the algorithm, K is there. So we're overwriting K. And if we want, we can swap, although this is not necessary, but maybe it makes it easier to understand. It's not necessary to do this, but let's just throw it in there anyway. So let's so K is in position. Let's use assertion here. We're going to say that because maybe this is easier for people to understand. So K is in position I. Once again, I'm trying to do it in a way that's not necessarily efficient but easy to understand. So inside the loop, at the very top of the loop, I is the position of where K is. And we'll verify that with an assertion. In fact, we can even do it like this, because K is in VI. We can do this. That's the same as comparing, K to VI minus 1. So if the thing that's in position I is less than the thing that's in position I minus 1, they're out of order. So we need to swap them. Actually, we know that this is K already. So we don't need a third element for the swapping. We take what's in position I minus 1, we put it into position I, and then we put what used to be in position I, which is always K, at the top of the loop, we push that into, or copy that into position I minus 1. So this is if I is a bad spot for K. What happens if that comparison is false? In other words, v of I is greater than or equal to v of I minus 1. That means the order is fine. Position I is a good spot. It's a good slot for K. So we're done. We don't have to do anything there. One thing is missing. Anybody spot it? At least I think one thing is missing. Does anyone know what I think is missing? Because I might be wrong. This loop is, will this loop terminate? That's one thing you should always check. Will the loop terminate? Well, you know, if I comes in as 4, if we don't change I, the loop condition is always true, and then we have an infinite loop. So this loop does not terminate. We'll need to decrement I. And we're done. Oh, we're running out of time. I can't believe it. Let's see if it works. V is not declared in this scope. That's line 11. Oh, it's V1. It should be V, not V1. Oh, we got to get out of here. Line 31. This a junk code in there? All tests passed? It works. We're done. Okay.